Now we come to module 4 of chapter 6. In this module, we shall learn two important results associated with Fourier transform, and also we shall learn what will be the Fourier transform in more than one dimension. The two important results associated with Fourier transform are convolution theorem and Parseval relation. First, we define what is convolution of two functions in minus infinity to plus infinity. The convolution of two functions small f(x) and small g(x), which is denoted by f star g and is defined by f star g x is equal to 1 by root 2 pi integral minus infinity to plus infinity f of x minus t into gt dt. This is the convolution of two functions f and g. Now we shall learn some properties of convolution of two functions. First property is that convolution of two functions is commutative. That means f star g of x is equal to g star f of x. Next property is the convolution is associative. That means f star g star h is equal to f star g star h. Next property is convolution is distributive. That means f star g plus h is equal to f star g plus f star h. Next we come to convolution theorem for Fourier transform. If curl f of f(x) is capital Fs, that means Fourier transform of small f(x) is capital Fs and Fourier transform of small gx is capital Gs, then number 1, Fourier transform of small f star g, that means Fourier transform of convolution of small f and g is equal to product of capital Fs and capital Gs. That means Fourier transform of convolution of two functions small f and small g is equal to product of their Fourier transform. Number 2, inverse Fourier transform of capital Fs and capital Gs, its product is equal to the convolution of small f and g. For proof, we first find out Fourier transform of convolution of small f and small g, that is curl f of f star g, that is given by 1 by root 2 pi minus infinity to plus infinity, again minus infinity to plus infinity integral f x minus t gt dt into e to the power I s x dx. Now we interchange the order of integration. We take out t integral as the outer integral and x integral as the inner integral, so that we get Fourier transform of f star g equal to 1 by 2 pi integral minus infinity to plus infinity gt dt integral minus infinity to plus infinity f x minus t e to the power I s x dx. Now in the inner integral we substitute x minus t as u, so that we get 1 by 2 pi integral minus infinity to plus infinity gt integral minus infinity to plus infinity small fu e to the power I s into u plus t du dt. So that we get 1 by root 2 pi integral minus infinity to plus infinity gt e to the power ist dt into 1 by root 2 pi integral minus infinity to plus infinity fu e to the power isu du. So, the first integral is Fourier transform of small gt and the second integral is Fourier transform of small fu. So, that we can write Fourier transform of f star g as capital Fs into capital Gs. So, the first part is proved. Similarly, we can prove the second part, that is Fourier inverse transform of capital Fs into Gs will give back the convolution of small f and g. Next we come to another important relation, that is Parseval's relation. Parseval's relation is given by integral minus infinity to plus infinity mod of small fx square dx. This is equal to integral minus infinity to plus infinity mod of capital Fs square ds. Now, for proof we consider the result 2 in the previous theorem, that is Fourier inverse of capital F into capital G, that gives back the convolution of small f and g. So, this is equivalent to left hand side is the Fourier inverse of product of capital F and capital G. So, that this is equal to integral minus infinity to plus infinity capital Fs into capital Gs e to the power minus Isx ds equal to integral minus infinity to plus infinity small f x minus t into gt dt. In this result, we put x equal to 0 and this produces integral minus infinity to plus infinity capital Fs into capital Gs ds. This is equal to integral minus infinity to plus infinity f of minus t into gt dt. This can be shown to be equal to integral minus infinity to plus infinity small f t g of minus t dt. In this result, we substitute gx equal to complex conjugate of f of minus x. Then from left hand side of this result we obtain, in the previous result we put gx equal to complex conjugate of small f of minus x, then capital Gs, which is the Fourier transform of small gx, and that is equal to 1 by root 2 pi integral minus infinity to plus infinity gt e to the power ist dt, and that is equal to 1 by root 2 pi integral minus infinity to plus infinity f of minus x bar into Isx dx. Now, this is equal to, by putting minus x equal to x, this becomes 1 by root 2 pi integral minus infinity to plus infinity f bar x e to the power minus I s x dx. So, minus I s x dx is the complex conjugate of e to the power I s x. So, that this result can be written as 1 by root 2 pi integral minus infinity to plus infinity complex conjugate of f x e to the power I s x dx, and that is equal to capital F bar s. So, we find that capital G s is equal to capital F bar s if we put small g x equal to small f bar minus x. Thus, in this result we obtain by putting capital G s equal to capital F bar s and small g x equal to small f bar minus x, we get integral minus infinity to plus infinity capital F s into capital F bar s ds. This is equal to minus infinity to plus infinity small f x into small f bar x dx, and this is equivalent to minus infinity to plus infinity small f bar x square dx, that is equal to integral from minus infinity to plus infinity mod of capital F s square ds. So, we proved the Parseval relation. Now, the general Parseval relation is integral minus infinity to plus infinity small f x into small g bar x dx is equal to integral minus infinity to plus infinity capital F s into capital G s bar ds. Here capital F s is the Fourier transform of small f x and capital G s is the Fourier transform of small g x, and bar denotes the complex conjugate. To prove this, we consider the expression on the right hand side, that is integral minus infinity to plus infinity capital F s g bar s ds. This is equal to 1 by 2 pi integral minus infinity to plus infinity capital F s is integral from minus infinity to plus infinity small f x e to the power I s x dx, and capital G s bar is integral from minus infinity to plus infinity g t e to the power I s t dt bar ds. So, this is equal to, if we consider the complex conjugate of e to the power I s t in the last integral as e to the power minus I s t. So, we can write this as 1 by 2 pi integral minus infinity to plus infinity integral minus infinity to plus infinity f x e to the power I s x dx into integral from minus infinity to plus infinity g bar t e to the power minus I s t dt ds. Now, we manipulate this step to get 1 by root 2 pi integral minus infinity to plus infinity g bar t into integral from minus infinity to plus infinity f x into integral from minus infinity to plus infinity e to the power I s x minus t ds dx dt. So, that we get the last step from the previous step by interchanging the order of integration. So, that outermost integral is t integral, inner integral is x integral, and innermost integral is s integral. Now, we consider the innermost integral, that is s integral. For that, we know that Fourier transform of 1, we have learnt in the previous modules that this is equal to root 2 pi delta s, that is 1 by 2 pi integral minus infinity to plus infinity e to the power I sx dx, which is the Fourier transform of 1, this is equal to delta function, that is delta s. So, instead of x, if we write x minus t, then we get integral minus infinity to plus infinity e to the power I s x minus t ds. This will give us twice pi delta of x minus t. Now, we consider the innermost integral, that is s integral. So, this integral, and if we consider this result, we can write integral of fs g bar s ds, that is equal to integral of small g bar t integral minus infinity to plus infinity small fx delta x minus t dx dt. That means the innermost integral here, this is delta x minus t, and we have substituted that here. Now, from the property of delta function, this inner integral, that is x integral, this is equal to ft, small ft. So, that we get the result integral minus infinity to plus infinity capital Fs capital G bar s ds, this is equal to integral from minus infinity to plus infinity G bar t into Ft dt. Next, we come to convolution theorem for Fourier cosine and sine transform. Let curl Fc of Fx, this denotes the Fourier cosine transform of small fx, and this is also denoted by capital Fcs and is defined as in root over 2 by pi integral 0 to infinity small fx cos sx dx and capital Fc of small gx, which is denoted by capital GCs, this is equal to root over 2 by pi integral 0 to infinity gx cos sx dx. Then we have the result integral 0 to infinity capital Fcs into capital GCs cos sx ds. This is equal to half of integral 0 to infinity small ft into small g x plus t plus small g mod x minus t dt. We shall prove this result. Now, we can see that the left hand side of this relation, that is this term, if we write capital FCS and capital GCS, we get left hand side equal to root over 2 by pi integral 0 to infinity capital GCS into integral 0 to infinity small ft cos st dt into cos sx ds. That is equal to, after interchanging the order of integration, root over 2 by pi integral ft, that is small ft, into integral 0 to infinity capital GCS cos st into cos sx ds into dt. Here we have changed the order of integration so that s integral becomes the inner integral and t integral becomes the outer integral. Now, we use the formula for cos st into cos sx and we write this step as half of integral 0 to infinity small ft into root over 2 by pi integral 0 to infinity capital GCS into cos s x plus t plus cos s x minus t ds dt. Now, integral 0 to infinity GCS, that is capital GCS into cos s x plus t, this gives back the after Fourier cosine inversion, this term gives back small g x plus t, and integral capital GCS cos s x minus t ds, this after Fourier cosine inversion will give back small g mod x minus t. So that we get the result half of integral f t into small g x plus t plus small g x minus t dt. So, we have proved this result for Fourier cosine transform. Now, in this result we put x equal to 0, so that the left hand side becomes equal to integral from 0 to infinity capital FCS into capital GCS ds, and right hand side becomes 0 to infinity small ft gt dt. Now, we set small gx equal to small f bar x to find capital GCS, which is the Fourier cosine transform of small gx. This is equal to root over 2 by pi integral 0 to infinity, instead of gx we substitute f bar x into cos sx dx. So that this gives root over 2 by pi integral 0 to infinity fx cos sx dx whole bar, that means complex conjugate of the whole integral, and that gives the complex conjugate of capital FCS, that means complex conjugate of Fourier cosine transform of small fx. So that we obtain Fourier cosine transform of small gx, that is capital GCS equal to capital FCS bar, if we set small gx equal to f small f bar x. So, this result gives, after using these results, we get integral 0 to infinity mod FCS square ds, this is equal to 0 to infinity mod of small fx square dx. This is the Parseval relation for Fourier cosine transform. So far we have learnt the important results concerned with Fourier transform, that is convolution theorem and Parseval relation. Now, we shall use these results to evaluate some important integrals. Now, we consider some examples. First example, let small fx equal to e to the power minus ax, where a positive, and small gx equal to e to the power minus bx, where b is also positive. Then we can find out the Fourier sine and cosine transforms of these two functions. We know the formula, and that gives capital FCS equal to root over 2 by pi a by a square plus x s square, and capital FSS is equal to root over 2 by pi s by a square plus s square, and similarly capital GCS is root over 2 by pi b by b square plus s square and capital GSS equal to root over 2 by pi s by b square plus s square. Now, using this result, we shall show that integral 0 to infinity ds by a square plus s square into b square plus s square, this is equal to pi by 2ab into a plus b, where a positive and b positive. Now, this can be proved by using the Parseval relation for cosine transform, which is given by integral 0 to infinity capital FCS into capital GCS ds. This is equal to integral 0 to infinity small ft into small gt dt. Now, we know that small ft and small gt, these are given by e to the power minus sx and e to the power minus bx. So that the integral on the right hand side, this is equal to integral 0 to infinity e to the power minus a plus bt dt, that is equal to 1 by a plus b. And the left hand side integral, if we substitute capital FCS and capital GCS from this relations, then we obtain left hand side is equal to 2 ab by pi integral 0 to infinity ds by a square plus s square into b square plus s square. So that equating left hand side and right hand side and simplifying, we get the integral from 0 to infinity ds by a square plus s square into b square plus s square equal to pi by 2ab into a plus b, a positive, b positive. Similarly, Parseval relation for sine transform can be obtained, and this is given by integral 0 to infinity capital Fs into capital GSS ds. This is equal to 0 to infinity small ft gt dt. Using this result and knowing small ft small gt and capital Fs and capital Gs, we find that integral from 0 to infinity s square ds divided by a square plus s square into b square plus s square, this gives pi by 2 into a plus b. So, these integrals are evaluated very simply by using Parseval relations for sine and cosine transforms, and these integrals can be derived by other methods also. Next we come to example 2. For a positive and x positive, prove that Fourier cosine and sine transform of e to the power minus ax x to the power n minus 1 r, we write together curl f of cs of the function e to the power minus ax into x to the power n minus 1, where curl f of c is the Fourier cosine transform and curl f of s is the Fourier sine transform. We write it together, and that will be equal to integral 2 by pi into integral 0 to infinity e to the power minus ax x to the power n minus 1 into cos sx or sin sx dx, and that gives the result in root over 2 by pi gamma n cos n theta by pi n or sin n theta by pi n, where a is r cos theta and s is r sin theta. Now, for solution, we have Fc curl Fc plus I of curl Fs of the function e to the power minus ax x to the power n minus 1, that gives us root over 2 by pi integral 0 to infinity e to the power minus ax x to the power n minus 1 into cos Sx plus I sin Sx, and this cos Sx plus I sin Sx, this is e to the power I Sx. So that we get root over 2 by pi integral 0 to infinity e to the power minus a minus is x x to the power n minus 1 dx. This is equal to root over 2 by pi minus 1 to the power n minus 1 d n minus 1 dz n minus 1 integral 0 to infinity e to the power minus zx dx. Here we substitute in this integral a minus is as z, so that this result can be written in this form. So, performing this integration, we obtain this is equal to root over 2 by pi minus 1 to the power n minus 1 dn minus 1 dzn minus 1 of 1 by z, and this can be expressed in terms of gamma function as root over 2 by pi gamma n by z to the power n. Now, putting back the value of z as a minus is, this gives root over 2 by pi gamma n divided by a minus is whole to the power n. So, this after some simplification will give back root over 2 by pi gamma n by r to the power n cos n theta plus I sin n theta, where in this step we have multiplied numerator and denominator by a plus is whole to the power n, so that we get the last line. Now, equating the real and imaginary parts from both sides, we get the desired result. Now, using this result, we can derive some apparently complicated integrals. For example, if we write the inverse cosine transform from this relation, we get e to the power minus ax x to the power n minus 1 as root over 2 by pi integral root over 2 by pi gamma n cos n theta by r to the power n cos Sx ds. Now, we know that we have taken in this example a as r cos theta and s as r sin theta, so that we can substitute instead of r using those results, and we obtain this integral as 2 by pi gamma n integral 0 to infinity cos n theta by a to the power n in cos to the power n theta into cos ax tan theta a sec square theta d theta. Here we have substituted s as given by r sin theta and we have eliminated r. So that this gives 2 by pi gamma n by a to the power n minus 1 integral 0 to pi by 2 cos n theta cos to the power n minus 2 theta cos of ax tan theta d theta. Now, we substitute a equal to 1 in the last result. So, that we get 0 to pi by 2 integral cos n theta cos n minus 2 theta cos x tan theta d theta equal to pi by 2 gamma n e to the power minus x to the power n minus 1. Similarly, one can show that for n greater than 1 and x positive, integral from 0 to pi by 2 sin n theta cos to the power n minus 2 theta sin x tan theta d theta, this is equal to pi by 2 gamma n into e to the power minus x into x to the power n minus 1. Next we come to example 3. Find the Fourier cosine transform of e to the power minus ax cos ax and e to the power minus ax sin ax, where a is positive, and hence obtain Fourier cosine transform of the function 1 by x to the power 4 k to the power 4 and x square divided by x to the power 4 plus k to the power 4, where k is positive. To solve this, we consider Fourier cosine transform of the function e to the power minus ax into cos ax plus I sin ax. Writing e to the power I ax for cos ax plus I sin ax, we get this is equal to Fourier cosine transform of the function e to the power minus a 1 plus I into x, and that is equal to root over 2 by pi integral 0 to infinity e to the power minus a 1 plus I x cos sx dx. Now, instead of cos sx, we write it as real part of e to the power minus j sx, where j is another imaginary unit which does not interact with the imaginary unit I. So, that we can write the Fourier cosine transform of e to the power minus ax cos ax plus sin I sin ax as root over 2 by pi real part with respect to j of the integral 0 to infinity e to the power minus a into 1 plus I minus js x dx. After performing the integration, this gives root over 2 by pi real part of j 1 by a into 1 plus I minus js. Multiplying numerator and denominator by a into 1 plus I plus js and taking the real part, this gives root over 2 by pi a into 1 plus I divided by 2 a square I plus s square. We have taken the real part with respect to j. Now, simplifying this with respect to I, we obtain integral 2 by pi a by 4 a4 plus s4 into s square minus 2 a square plus I into s square plus 2 s square. So, that taking the real and imaginary part, we obtain Fourier cosine transform of e to the power minus ax cos ax is equal to root over 2 by pi a into s square minus 2s a square divided by 4 a4 plus s4, and Fourier cosine transform of e to the power minus ax sin ax as root over 2 by pi a into s square plus 2s a square divided by 4 a4 plus s to the power 4. Now, by addition and subtraction, we obtain a into s square divided by 4a4 plus s4. This gives root over 2 by pi into Fourier cosine transform of the function e to the power minus ax into sin ax plus cos ax. Similarly, by subtraction of these two, we get 4a cube by 4a4 plus s4 equal to root over 2 by pi Fourier cosine transform of e to the power minus ax sin ax minus cos ax. So, using the Fourier cosine inversion in relation 2, that means this relation, we obtain integral from 0 to infinity 4a cube by 4a to the power 4 plus s4 cos sx ds. This is equal to pi by 2 e to the power minus ax into sin ax minus cos ax. Now, we substitute 2a square equal to k square, where a is equal to k by root 2, k is another constant, and interchange x with s. So, we get the left hand side as integral from 0 to infinity cos sx dx divided by x square plus k4. This is equal to pi by 2 root 2 k cube into e to the power minus ks by root 2 into sin ks by root 2 minus cos ks by root 2. So, this gives the Fourier cosine transform of the function dx by x square plus k x4 plus k4. Similarly, from relation 1, we find after inverse Fourier cosine transform, integral 0 to infinity x square cos sx divided by x4 plus k4 dx. This is equal to pi by 2 e to the power minus ks by root 2 into sin ks by root 2 plus cos ks by root 2. So, we have obtained the results. Now, we come to Fourier transforms in 2 or more dimensions. Fourier transform pair for a function fx in one variable is, we know, capital Fs equal to 1 by root 2 pi integral minus infinity to plus infinity small fx e to the power I sx dx, and its inverse transform is given by small fx equal to 1 by root 2 pi integral from minus infinity to plus infinity capital Fs into e to the power minus I sx ds. This can be extended to a function f, function of two variables x1 and x2, and this is given by capital F s1 s2 equal to 1 by root 2 pi integral minus infinity to plus infinity, again integral minus infinity to plus infinity small f x1 x2 into e to the power I s1 x1 plus s2 x2 into dx1 dx2, and its inverse transform is given by small f x1 x2 equal to 1 by root 2 pi integral minus infinity to plus infinity, again integral minus infinity to plus infinity capital F s1 s2 e to the power I small s1 x1 plus small s2 x2 ds1 ds2. Now, for function of n variables x1 x2 up to xn, this Fourier transform can be extended as given by capital Fs, which is the Fourier transform of capital small f of capital X. Capital X is the vector x1 x2 up to xn, and that is given by 1 by root 2 pi to the power n by 2 n integrals from minus infinity to plus infinity small f of capital X into e to the power I s capital X into dx1 dx2 up to dxn. Similarly, the inverse transform is defined in this form, where here capital X denotes the vector in n dimensional space having Cartesian component small x1, small x2 up to small xn, and capital S is the similar vector having component small k1, small k2 up to small kn. So, in this module we have learned two important results associated with Fourier transforms, and we have also learned the Fourier transform in higher dimension. With this, I conclude module 4 of chapter 6.